Hello, my name is Kuruppu Rodrigo and welcome to my Aerofoil and Wing design presentation. I have divided this presentation into 7 sections where each section will provide details of the design process until it's finished. Starting with design activity 1. Defining my wing requirements so that the design would support a specified requirements of an aircraft that's operating at a specific flight condition. I use my serial number as reference to generate my requirements. First, the aircraft type, which happen to be in the close air support fighter jet category. Next, defining the flight conditions which the aircraft is flying. Using my serial number as reference, I managed to calculate the cruising speed, altitude, and all-up weight of the aircraft. After that, I decided to do some background research on my assigned aircraft type, where I found out about the A-10 Thunderbolt II. This aircraft matched the description of my design requirements as well as the aircraft type, so I decided to base my design using the A-10 as reference. The A-10 is the US Fire Force's primarily low altitude close air support aircraft, also best known for its 30mm Gatling gun mounted on the nose. The GAU Gatling gun is designed to fire armor-piercing, depleted uranium, and highly explosive incendiary rounds. With all the all of its weight and firepower on board, A-10 has excellent maneuverability and at low speeds and altitudes. Reading more about the A-10 sparked my interest to find more about its characteristics and design, which led to me basing my aerofoil design and wing design of the A-10. Moving on to design activity 2. In this design activity, my objective is to design the aerofoil to create the wing, and that will be driven by the design requirements established in the previous design activity. First, it was necessary for me to establish the shape of the wing so that the lift characteristic can achieve the design requirements. From this, detailed design of the airfoil can begin. First, I used the information that I found from the research and to determine the characters of my wing design. Then I proceeded to identify the characters where I choose the symmetrical monoplane design, wing design as my primary design choice. This was due to the similarities between my wing design and the A-10. Next, I had to determine more flying conditions and parameters. These were air density, air temperature, air pressure, lift coefficient, lift force, wing loading, stall speed, and max lift coefficient. To save time, I decided to use an online library to help determine the air density, air pressure, and the air temperature, where it had detailed tables highlighting specific flight conditions at specific altitudes. The rest of the calculations were done using the provided equations to establish more design requirements. However, at this time, because of the wing platform was unknown, I used an estimated value to calculate the wing loading, stall speed, and a maximum lift coefficient. These design requirements will be finalized at later stages of the design process. In design activity 3, the fundamental shape of an airfoil is key to the overall performance of the wing. Its sensible design is therefore crucial to maximize the performance of the wing. Since the aircraft will be spending most of its time in cruise, the drag should be minimized as much as possible. It is this flight phase where I will be designing my aerofoil and wingfoil. At this point, it was important for me to determine the ideal lift coefficient for my aerofoil as well as the aspect ratio. However, the aspect ratio that I calculated here was only an estimate due to having an estimated wingspan. By calculating these two parameters, it is then possible to identify the geometry of my airfoil, the mean camber line thickness distribution, leading edge radius, and the trailing edge angle. All of these geometric characteristics contribute to a min-max in the performance of the airfoil and the wing. Once I familiarized myself with the characteristics, I was then It was then I decided to look for a baseline airfoil where I could potentially take reference from. Using the A10 Wing airfoil as guidance and looking through the airfoil databases, I selected a 6-digit NACA airfoil. Advantages of these aerofoils are that they have high maximum lift coefficient, very low drag overall, maximum small range of operating conditions, and optimized for high speeds. Disadvantages include high drag out of optimum range of operating conditions, which is neglected as close air support jets aren't meant to operate beyond optimum range. High pitching moment, poor stall behaviors, and very susceptible to softer surface roughness. Next, in design activity 4, it was time to perform a baseline analysis on the airfoil to determine what adjustments and modifications that are needed to be done to meet the design requirements using XFLR5. However, to conduct the analysis, I had to specify the Reynolds number, Mach number, and the dynamic viscosity. The analysis showed that the aerofoil doesn't produce as much lift, thus the maximum camber had to be increased. The analysis also highlighted major flaws where it either underperformed compared to its type characteristics or doesn't function at all. Therefore, I modified the airfoil by adjusting the camber thickness using the XFLR5 inverse design function. After analyzing multiple modifications to the camber, I finalized on a shape that performs well enough to meet the design requirements. The analysis highlights major differences between the two airfoils and that the modified airfoil is capable of meeting the design requirements. Moving on to design activity 5, after finalizing the modified airfoil, I proceeded to produce a 3D model of the airfoil. To 3D print my design, I had to produce a 3-dimensional spline in Excel of the airfoil. Then I used CATIA to produce a 3D model. And then I made significant alterations to reduce the size of the airfoil. Once I was satisfied with the model, I moved it onto a 3D printing software and I prepared it to 3D print. Here are some pictures of my airfoil being 3D printed. And here is the final 3D printed model of the airfoil. Moving on to design activity 6, to proceed to the wing analysis, I had to determine all the parameters that I couldn't calculate before, as well as geometric characteristics to determine the wing geometry. Many geometric characteristics were negligible as my aerofoil was based off the A10, which uses a monoplane straight wing type. Therefore, my wing design ultimately formed to be a rectangular shaped wing, as its main purpose was to meet the design requirements. Thus, I decided to not add any taper, sweep angle, or dihedrals. Finally, in design activity 7, I analyzed and determined whether the wing is capable of meeting the design requirements. I had to create my wing using the XFLR5, where I performed multiple analysis using the define analysis function. After defining and analyzing the wing, these graphs are produced, highlight the ideal angle of attack for the ideal lift coefficient to meet the design requirements. Thus, I am able to finalize my wing and airfoil design as it meets the design requirements and the flight conditions that I have determined previously in the previous design activities. In conclusion, this small project helped me understand the various techniques used when designing and creating the airfoil or wing. However, if I had been given more time, I would have been able to provide more detailed justifications for my design choices, which would include all the small, minute design choices I've made and give more in-depth explanations to the analysis that I've conducted using the XFLR5. And thus concludes the presentation about my design process. Thank you for your time.